Hi students, good morning, welcome back to our physics classes. So during the last class we have started with kinetic theory of gases, and we have seen the postulates of kinetic theory of gases, and we have defined or derived the equation for the pressure exerted by a gas in the walls of the container. And that equation that I suppose you are remembering, that P is equal to 1 by 3 rho V square, where rho is the density, density, and V is the RMS velocity. That means root mean square velocity. So we define the root mean square velocity also from that equation. So that we have stopped with. And now we can continue with the same equation. P is equal to 1 by 3 rho V square, and rho you can write it as 1 is equal to 1 by 3 m into n divided by V into V square average. This is the actual equation for finding the pressure exerted by a gas. And this Mn is the total mass and V is the volume. So we can say that PV is equal to 1 by 3 M into N into V average square. So for a particular temperature, the velocity remains constant. Particular temperature, the root mean square velocity remains constant, which means at constant temperature PV equal to 1 by 3 is constant, M is constant, N is constant, and V is also constant. We can say that PV equal to a constant PV is a constant provided the temperature remains constant. So we can say that is the proof for Boyle's law. Boyle's law states that at constant temperature PV is equal to constant, that is P and V are inversely proportional. So PV is equal to a constant. So that is the explanation of Boyle's law. You can say that is the explanation of Boyle's law. So that gives a relation between temperature and velocity. Velocity means our RMS velocity, root mean square velocity. So in kinetic energy, average kinetic energy is taken as temperature. So there is a relation between temperature and velocity of the particles in a gaseous system. So we are trying to prove or trying to show that the RMS velocity is proportional to, or it is related to temperature. For that again we can have the same equation. P is equal to M into N divided by V into V square average, where N is the Avogadro number. So from that it is clear that we have taken 1 mole of gas. So in 1 mole of gas there are n number of particles. So Mn divided by V into V square will be P. So we can have PV is equal to 1 by 3 into M into V square average. What is this M? That is a molecular mass. So small m into capital N you can take it as molecular mass. So PV is equal to 1 by 3 mv square. So PV you can take it as RT. According to ideal gas equation, PV is equal to N mu RT, where mu is the number of moles. Here we have taken only 1 mole, so that will become RT. So RT is equal to 1 by 3 m into V square. So you can write here V square average is equal to 3 RT divided by M. Okay, so V square, V RMS will be, when you are taking the root, that will be RMS velocity. So V RMS is equal to root of 3 RT divided by M. From this 3 is constant, R is constant, M is constant, and T is only the variable. So we can say that V RMS proportional to root C. That is the kinetic interpretation of temperature. That means temperature increases, the kinetic property of the gas molecules increases. From this equation, we can have the relation between RMS velocity and the molecular mass. Suppose we are having two gases with the molecular masses M1 and M2, and their RMS velocities are V1 RMS and V2 RMS. So we can say that V1 RMS is equal to root of 3 RT divided by M1, and V2 RMS is equal to root of 3 RT divided by M2. So when you are taking V1 by V2, that is V RMS of V1 divided by V2, when you are taking V1 divided by root 2, it will be root of M2 divided by M1. Root of M2 divided by M1. So that is the relation between RMS velocity and molecular mass. Expression shows the relation between RMS velocity and the molecular mass. Again, if you have a 1 mole of a gas, its molecular mass is M, and its velocity, that RMS velocity, average velocity is V RMS. So we can have its kinetic energy. Kinetic energy K is equal to half M into V square. Half M into V average square. And this half M V square you can write from this expression. So here we have mv square is equal to 3 RT. So half mv square will be 3 by 2 RT. So which is equal to 3 by 2 RT. Half mv square is equal to 3 by 2 RT. So we can have, this is the kinetic energy of 1 mole of gas. It is the kinetic energy of 1 mole of gas. In 1 mole, how many particles are there? Capital N number of particles are there. So you can find out the average kinetic energy. You can find out the average kinetic energy. How you can find out the average kinetic energy? That is QAE divided by N, which is equal to 3 by 2 RT divided by N. Last class we have that relation, that is RT is equal to K, the Boltzmann constant. So you will get that 3 by 2 K, 3 by 2 K. That means average kinetic energy of a particle in a gaseous system is given by average kinetic energy. It is not the total kinetic energy, it is the average kinetic energy, Ke by N, which is equal to 3 by 2 K. That is average kinetic energy is equal to expressing that is in conical bracket, that is average value. So average kinetic energy will be 3 by 2 Kt. Okay, so here we have the relation between temperature and RMS velocity and molecular mass, temperature and kinetic energy. Okay, relation between temperature and RMS velocity, temperature and average kinetic energy, and RMS velocity and the molecular mass. Okay. Again, we can have the same equation for the pressure. P is equal to 1 by 3 into m into n into v square average divided by v. Okay, this is a given mass of gas. It is not 1 mole, it is given mass of gas, and the mass of one particle is m, and n is the total number of particles in that system. So we can write v equal to 1 by 3 into n by p into m v square. Okay, no change at all. And you can have 1 by 3 into n by p into 2 into 1 by 2 m v square. What is this half m v square? Half m v square is the average kinetic energy. Average kinetic energy of a single particle. And average kinetic energy is 3 by 2 kT. So that will become 1 by 3 into n by p into 3 by 2 kT. So 3 and 3 get cancelled, multiplied by 2 is here, 2 and 2 get cancelled. That will become nkt divided by p. V equal to nkt divided by p. At constant pressure, V and T are directly proportional. At constant pressure, V and T are directly proportional. What is that? That is your Charles law. Okay, so at constant pressure, we can say that V and T are directly proportional. So V proportional to T at constant pressure. So that is Charles law. Boyle's law we have already seen, and this is the proof for Charles law. Okay, again, from the same equation, PV is equal to 1 by 3 into MNV average square. And we are having two different gases at the same temperature and pressure. Two different gases at the same temperature and pressure. So at the same temperature and pressure, equal volume of different gases contain equal number of particles. Okay, so when you are having PV is equal to M1, N1, V average, V1 square, and for another gas 1 by 3 into M2, N2, V2 square. Okay, at constant temperature and pressure, equal volume of gases contain equal number of particles. What is that? That is our Avogadro's law. So Charles law we have seen, Boyle's law we have seen, and another gas law is the Avogadro's law. So Avogadro's law says at constant temperature and pressure, see the pressure is same, equal volume of gas. Equal volumes are there. So 1 by 3 when you are comparing these, we can write that M1, N1, V1 average square is equal to M2, N2, V2 average square. Okay. Provided at constant temperature and pressure, equal volume of gases contain equal number of particles. So here, at constant temperature, what happens when the temperature also remains the same? Their average kinetic energy is also same. So we can say that at constant temperature, half M1 V1 square is equal to half M2 V2 square. So M1 V1 square and M2 V2 square are equal. So that will say remaining N1 equal to means at constant temperature and pressure, equal volume of all the gases contains equal number of particles. That is Avogadro's. That also here proved. Okay, so from the same equation for pressure, P is equal to 1 by 3 M into N divided by V into V average square. From that equation, we have got the gas laws proved, and we have the relation between velocity and temperature, velocity and molecular mass, and temperature and kinetic energy. So that is the importance of that equation for the pressure exerted by a gaseous system. Okay, now we have said that whenever the particles, when you consider a gaseous system, that gaseous system contains tiny identical rigid particles, and these particles are in random motion. And as they travel, they can carry energy also, which means the probable ways of movement is similar to the probable ways of transferring energy. Okay, so when you consider a single particle, that means a monoatomic gas. So suppose when you are considering a monoatomic gas, its molecule contains only one atom. Gas molecule contains one atom. And that atom, when you consider that is in a volume, that atom can travel either in x direction, either in y direction, or either in z direction. You can have three possible ways of traveling. And total number of ways of traveling, or total number of ways of transfer of energy, that is known as degree of freedom. Degree of freedom. And it is expressed as F. And for a monoatomic gas, we can say F is equal to 3. That means it has three possible ways of movement and three possible ways of heat transfer. And suppose you are having a diatomic molecule. A diatomic molecule. When you consider a diatomic molecule, this diatomic molecule as a whole it can move along its direction, as a whole it can move along y direction, as a whole it can move along z direction. That means already it has 3 degrees of freedom. Plus it can rotate also. Suppose this is that diatomic molecule, it can travel along x direction, along y direction and along z direction, and it can rotate about its axis or perpendicular to its axis in both the ways. Okay, so it has three rotational motion also, but it's a moment of inertia about or what we can say, yes, it's a moment of inertia about its own axis is very less. So about its own axis, the transfer of heat energy, transfer of energy is also very negligible. So we can say that it has three possible translatory motion along x direction, y direction, z direction, plus two rotatory motion also. Third one is also there, but we are not considering that along the axis. So we can have three translatory plus two rotator. So what will happen? It can have 5 degrees of freedom. F is equal to 5. Are you getting me? That is a possible ways of travel, movement, or possible ways of heat transfer. That is degree of freedom. So any polyatomic molecule, when you are considering, they are having 3 translatory as well as 3 rotatory. So it has 6 degrees of freedom. Okay. So when you are considering, we are already said that it is having energy and it carries energy as it moves. So how this energy are related to the possible ways of movement, which means average kinetic energy of a single particle is equally distributed along its degrees of freedom. Average kinetic energy of a particle or a system is equally distributed along its degrees of freedom. That is known as equipartition theorem. That is known as the equipartition. That is very important term. Equipartition theorem. Average kinetic energy of a gas molecule is equally distributed along its degrees of freedom. Along its degrees of freedom. So I will give you an example. We have seen for a monoatomic gas or a single gas molecule or a single gas particle, the average kinetic energy is given by 3 by 2 kT. We have already said that. We have already seen that. 3 by 2 kT. And this is the average kinetic energy of a single particle. And it has, since it is a single particle, it has 3 degrees of freedom. So it can be taken as 1 by 2 into kT into F. What is F? Degree of freedom. So the total energy will be U is equal to 1 by 2 FKT. That is, average kinetic energy of a system will be 1 by 2 FKT. Gaseous system will be 1 by 2 FKT, where F is the degree of freedom. Where F is the degree of freedom. Okay, so average kinetic energy per degree of freedom will be 1 by 2 kT. Average kinetic energy per degree of freedom will be 1 by 2 kT, and the total kinetic energy will be 1 by 2 FKT. 1 by 2 FKT. That 1 by 2 FKT is for a single particle. Average total energy of a single particle is 1 by 2 FKT. But remember, if you consider 1 mole of gas, how many particles are there? N particles are there. So we can say that total internal energy of the system will be 1 by 2 FKT multiplied by N. And K into N is equal to R. So that is 1 by 2 FRT. Okay. So average kinetic energy of a particle per degree of freedom is 1 by 2 kT. Average kinetic energy of a single particle in all possible ways will be 1 by 2 FKT. If there are n particles, the total internal energy will be 1 by 2 FKT multiplied by n, where K into n is equal to R. So that will be 1 by 2 FRT. Okay. So we have seen what is the total energy of a gaseous system of 1 mole of gas. So that will be u is equal to 1 by 2 FRT. Differentiate with the t. So du by dt is equal to 1 by 2 FR. Du by dt is equal to 1 by 2 FR. And you know, du, change in kinetic energy, change in internal energy is equal to Cv into dt. From first law of thermodynamics, we have du is equal to Cv into dt. So du by dt is equal to Cv. Is it? So Cv is equal to 1 by 2 Fr. Then we are having the relation Cp minus Cv is equal to R. So Cp is equal to Cv plus R. So Cp is equal to, what is Cv? 1 by 2 Fr plus R. That will become R into 1 by 2 F plus 1. Okay, so this is Cp and this is Cv. Cv is equal to 1 by 2 Fr and Cp is equal to 1 by 2 Fr plus R. That is R into 1 plus F by 2. When you are knowing Cp and Cv, you can have gamma. Gamma is equal to Cp by Cv. Gamma is equal to Cp by Cv. And you can have, for a monoatomic gas, F is equal to 3. So Cv is equal to 3 by 2 R and Cp is equal to 3 by 2 R plus R. That means 5 R by 2. Is it? So Cp by Cv will be 5 R by 2 divided by 3 R by 2. That means 5 by 3. Cp by Cv for monoatomic gas will be 5 by 3. And diatomic, you can find out what is the gamma for diatomic gas and triatomic gas. For diatomic gas, F is equal to 5 and triatomic gas it will be 6. So for diatomic gas, it will be 7 by 5 and triatomic gas it will be 4 by 3. That you can easily calculate using this equation Cp by Cv, where Cv is 1 by 2 Fr and Cp is R into F by 2 plus 1. So remember this equation. In sometimes in the numericals, gamma value will not be given, and it mentioned that it is a triatomic gas. So gamma you can easily find out. Cp by Cv you can find out by calculating what is the value of Cp, what is the value of Cv, and Cp by Cv you can easily calculate that. Okay, so that is degrees of freedom and relation between Cp and Cv in terms of degrees of freedom. Okay, so that's all for today, and we will meet in the next class.